This tutorial will help you learn the steps in determining an empirical formula and a molecular formula. And as you should have read, an empirical formula is a formula with the simplest whole number ratios in a particular compound, and is usually a general formula or ratio of atoms to one another for many different kinds of compounds that happen to be in a group. A molecular formula is actually a lot more specific for a non-simplified ratio of atoms to one another, and that's of course specific for one particular compound. So in the case of this example, we're given percentages, and typically that's how empirical formula questions begin, is you're given percentages, and then from those percentages we can help determine the ratio of the particular atoms to one another in an empirical formula. And then we can use that information to help determine what the actual molecular formula is. So here we have carbon, hydrogen, and oxygen, and they are the components of this particular compound. We'll use those values then to help us determine what the ratio of carbons, hydrogens, and oxygens are to one another in the empirical formula. And once we have that simplified ratio, we can then use some other information to help determine what the molecular formula is, meaning what specific number of carbons, hydrogens, and oxygens are present in this particular compound. Because as you know, different numbers of atoms means a different formula, and then of course a different compound. And that of course is the law of definite proportions, that every compound has a fixed ratio of atoms. So let's go ahead and get started. Here are these steps, of course, in helping you to determine the empirical formula. And as I said, typically you're given percentages, and those percentages we then convert directly one-to-one into grams. And that's because we assume that we have 100 grams, and since every percentage adds up to 100% total, the ratio kind of stays the same. So it's very easy just to make the percentages your grams and then go from there. So that's really step one. Step two is to determine the actual ratio. And of course that ratio, or that unit value, is the mole. And of course the way we determine that is by dividing that gram amount by the atomic mass of the atom. Okay? And then from there we can simplify. So let's take a look at this example before we get any further into the steps. It asks to determine the empirical formula of a compound which contains 40% carbon, 6.7% hydrogen, and 53.3% oxygen. And of course this ratio is probably very familiar to you, or these percentages should be. And that's because we're just working with the same numbers so that we hopefully become familiar with them and then make this whole learning experience come full circle in this chapter. So if we take our 40% and make that 40 grams, and 6.7% and make 6.7 grams, and 53.3% and make 53.3 grams, from there we can move on to step two, which is dividing each atom by its atomic mass. And of course you can locate the atomic mass of each element on the periodic table. The atomic mass of carbon is 12, so 40 divided by 12 would give us 3.33 mole units. 6.7 grams of hydrogen divided by 1 gram, because 1 gram is the atomic mass of hydrogen on the periodic table, and that would give us 6.7 moles. And then 53.3 grams divided by 16, which is the atomic mass of oxygen, and that will give us 3.33 moles. So there we go. We have our ratios of 3.33 to 6.7 to 3.33. That is, of course, neither simplified nor whole number, so we have some more work to do before we can actually count this as an empirical formula. So let's pick up where we left off on step three. Simplify the ratios that are calculated in step two by dividing each value by the smallest value. So that means we're going to divide all of these by the smallest number. Well, the smallest value between 3.33 and 6.7 would be 3.33. So we'll divide all three of these values by 3.33, as we've done in this step, and when divided by itself we get 1. 6.7 divided by 3.33 is approximately 2, and again 3.33 divided by itself is 1. So again, we want to divide by the smallest number, typically the same as one of these particular values, and we'll always end up with 1, and you can't get more simplified than 1. Alright, luckily we've got a very simplified ratio, can't get more simple than 1, as I said, and they are all whole numbers, so that's great. Step 4 says you will likely have a simplified whole number ratio, which we do, and that of course is the empirical formula. Alright, we'll rewrite the formula now, knowing that we have 1 carbon, 2 hydrogens, and 1 oxygen, and that would mean that our empirical formula is indeed C1H2O1, or CH2O. Now, if you happen to have a situation where, hypothetically speaking, you did not end up with a whole number value right here, and you ended up with, let's say, 1.5, hypothetically speaking. Of course, you couldn't leave it that way. You would have to move on to step 6, which would be that you'd have to multiply this value by something else. Don't go too crazy. Start off with 2, 3, 4, because we don't want to undo the simplification process. What we want to do is make this whole number. So if this was 1.5, I'd multiply maybe by 2, and that would give me 3, and that would be a whole number. And then, of course, I'd have to do the same thing for all of these. Multiply by 2, and then multiply again by 2, and then I would have a 3 to 4 to 2 ratio, which again is still simplified, but it still is now a whole number, because we couldn't just leave that 1.5 by itself. You can't have a subscript that is decimal in value. So you do need to adjust that if that happens, but again, choose very small values, 2, 3, something like the examples given here in step 6, to help attain a whole number value, but don't go overboard, because you will ruin the simplification process that you had already achieved. So this was a nice, easy example. We got an empirical formula that worked out quite nicely, CH2O, and from there we can move on to converting that empirical formula into a molecular formula, which is simply a multiple of the empirical formula. So the first thing we need to do is find the mass of the empirical formula, and we're going to go ahead and do that right down here. Our empirical formula was CH2O, and the mass of that would be, of course, the mass of C, which is 12, the mass of 2 hydrogens, that's 2 times 1 because they're 1 apiece, and the mass of oxygen, which is 16. So add that together, and one empirical formula, 1 CH2O, would weigh 30 grams. All right, great. Now, hopefully that additional piece of information that we need is provided in the problem, and that should be the molecular weight, and of course it is given right there in the problem. And then last of all, we solve the problem. So let's take a look at this example. What is the molecular formula of the compound above if the molecular weight is 180 grams? So we're given that molecular weight, which is 180 grams, and based on the first 2 steps I've just went over, we have to find the mass of the empirical formula, which we did, which is 30 grams. And step 2 asks us to divide the molecular weight, or the molecular mass, which is given here in the problem as 180, by the empirical weight, or the empirical mass, which we calculate to be 30 grams. So 180 divided by 30 is 6. The reason, again, is the molecular formula is a multiple of the empirical formula. So we want to know how many times the empirical formula is the molecular formula. How many times bigger is it? Well, if we want to know the ratio, how many times bigger, we can take the ratio of the masses, which is 180 to 30, and that's a 6-fold difference. So we know that the molecular formula is 6 times the empirical formula. So we'll now move on to step number 3, that is to multiply the empirical formula by the multiple we calculated here in step 2, which was 6. So here's our empirical formula, CH2O times 6. So C1 times 6 is C6. H2 times 6 is H12. O1 times 6 is O6, and there we go. And if you actually look at C6H12O6 and you calculate the mass of that, the formula weight, 6 carbons, 12 hydrogens, and 6 oxygens, then you should attain the 180 molecular weight value given in the problem, and double check yourself.